go through some mathematical exercises, very simple exercises to identify the natures of certain partial differential equations. So, we will give one example each of these equations which are very common in fundamental science and engineering applications. So, let us take an example. Del square phi equal to 0. This is perhaps the most simple but most commonly encountered partial differential equation in mathematical physics, which is known as Laplace equation. So, this Laplace equation is a prototype of many physical problems, like let us try to give some example. Like one of the possible examples is if you have steady state 2 dimensional heat conduction. So, you have instead of phi you have the temperature as the variable. Say let us consider there is no heat source and the material has uniform thermal conductivity. So, then it is del square T equal to 0, or you could have electrical potential distribution within a charge system. So, that also may be governed by the Laplace equation. There are many examples. For example, velocity potential distribution in an irrotational flow, that also is governed by the Laplace equation. So, there are different fields, different applications, physics changes, but what remains the same is the prototype, that Laplacian of some variable that is equal to 0. So, this is a very important equation. Let us try to assess that what is the particular nature of this equation. Is it parabolic, is it elliptic, or is it hyperbolic? So, let us consider a 2 dimensional example. So, if you try to figure out what is its particular nature, you have A equal to 1, B equal to 0, C equal to 1. So, what is B square minus 4AC? So, minus 4. So, that means it is elliptic equation. The big question is elliptic equation, so what? We understand that this equation is elliptic, but what physical meaning does it carry? Let us try to answer that. So, let us try to take an example of a heat conduction problem. Let us say that there is a domain, throughout the domain there is a uniform temperature, say the entire domain is at a temperature of 30 degrees centigrade. Now suddenly you heat some location of the domain, so that as if there is some heat source which is existing at some point of the domain, and you are activating this heat source, maybe it is an electrically heated situation, so that the domain gets heated up at that location. That means what you are doing? You are disturbing the initial temperature profile. So, once you are disturbing it, this disturbance will propagate to other points in the domain, and when it is elliptic, this disturbance propagates at all directions inside the domain, towards all directions inside the domain, and it does so at infinite speed. That is very important. So, this is one of the very important physical meanings that is being conveyed by the Fourier's law of heat conduction, that when you have a thermal disturbance, the thermal disturbance propagates towards all possible directions at infinite speed. So that means what, therefore what does this disturbance propagation try to do? It tries to nullify the difference in temperature between different points in the domain. So it tries to bring the domain to a homogeneous temperature, because there is a gradient of temperature, there is a messenger that goes from one point to the another point in terms of a disturbance, and that disturbance essentially tries to nullify the temperature differences between different points of the domain. So if you have disturbance at a point, that would be felt anywhere and everywhere. So if you are considering a numerical solution strategy, then you have to be careful that if you have a particular point, then this point should be, temperature at this point should be influenced by all its neighbors, because the disturbances propagate in all directions. So if you are writing a numerical system of equations where you have some neighboring points and you have a point under concern, then the point under concern should be influenced by all the neighbors. There is no exception to that. The other important thing is that for this elliptic type of problems, you have to specify boundary condition over the entire part of the domain. So the boundary condition may be of different types, we will come across the different types of boundary conditions subsequently, because numerical solution of equations is a strong function of the boundary conditions. So you could have different types of boundary conditions. Let us say that over some part of the boundary you have a particular temperature, and over the other part of the boundary you have a different temperature. That is possible. Say one part of the boundary you keep immersed in steam at 100 degree centigrade, another part of the boundary you keep immersed in ice at 0 degree centigrade. So they are at different temperatures. That means you have some discontinuities in the boundary condition, but the solution in the solution domain is continuous. So despite the possibility of discontinuity in the boundary condition, you will always have, for an elliptic problem, the solution continuous inside the domain. So there is no possibility of a discontinuity of the solution inside the domain. That is one blessing for selection of the, or for designing of the numerical method, that you do not have to account for any possibility of discontinuity in the solution domain. Why does it happen in such a way? Because the disturbance propagates at infinite speed in all possible directions. So that whatever is the discontinuity imposed by the boundary condition, that is very easily being countered by a very rapid disturbance message propagation from one point to another point to smoothen out any possibility of discontinuity. And this type of problem is also known as a boundary value problem, because you have to specify the boundary condition over the entire domain boundary to solve this problem. We will later on see that what types of boundary condition you could possibly impose, but first and foremost it is important to appreciate that you need to specify boundary conditions over the entire domain boundary. So this is one example. Let us consider another example. This is an example where we have physically put two variables, but only one highest order partial derivative term. This is an example of a one dimensional unsteady state heat conduction. If you put temperature in place of phi, and this alpha is nothing but the thermal diffusivity. So So let us try to understand what are the features of this partial differential equation. So here only the highest order derivative will matter. So A is equal to alpha, B is equal to 0, C is equal to 0. So B square minus 4AC equal to 0. So it has only one real characteristic, that means it is parabolic. Again the question comes, so what? So what does it physically signify? Let us consider these t and x as two physical variables and try to appreciate or analyze the situation from that perspective. So let us consider that there is a domain this is say x equal to 0, this is x equal to L, and we plot time along the vertical axis. So in this domain we are interested to see that how the temperature varies as a function of position and time. If you see that we are having an event at a particular time, say right now an event is occurring, some event is occurring, say at some temperature at some time, say t equal to T0, you are creating a thermal disturbance. So as an example, say that you have a one dimensional rod which is at a uniform temperature, at time t equal to T0 you are suddenly creating a disturbance by maintaining one end of the rod at a different temperature than the other end. So initially say the entire rod is at 0 degree centigrade, now suddenly you subject this boundary at x equal to 0 to a temperature of 100 degree centigrade. It is an abrupt discontinuity at time t equal to T0. So this is a disturbance when this boundary was not when this boundary temperature was not changed, everything was at 0 degree centigrade. Now you are creating a disturbance, you expect the disturbance to propagate. In what direction it will propagate? It will definitely always propagate in a direction forward in time. So what it will do? It will influence what will happen in the subsequent times. At t equal to T0 if you have created a disturbance, that disturbance will influence what will happen for t greater than T0, but it cannot influence back what has already happened some time back. So time is like a one way coordinate system. So there is a special characteristic of the time coordinate system, it is a unidirectional coordinate system. We will later on see that if you combine time with space, that need not anymore be a one way coordinate system, or we will also see certain example where space can also behave like a one way coordinate system. It is not always necessary that time is the only example of a one way coordinate system, but it is intuitively more obvious to consider as a time as a one way coordinate system. How we can understand it? We can simply tell it in this way, that whatever is happening now can only influence what will happen in the future, but it cannot influence what has already happened in the past. So whatever has happened in the past, that cannot be changed, or that cannot be influenced by what we are doing now, but we can always influence something which will happen in the future by what we are doing now. So that is how time is always a forward marching type of coordinate. So these types of problems we call as time marching problems. So time marching problems will have only one type of discontinuity, that is a discontinuity with respect to that reference time at which the disturbance is imposed, because before that time and after that time is physically a totally different type of domain. So how these are related? If you have a disturbance at a point and if you see that that disturbance is propagated at different locations, so you have some domain of disturbance and this domain of disturbance has its influence felt at certain locations. So domain of disturbance and domain of influence, these are two very important domains. So domain of disturbance is where you are imposing the disturbance, where you can impose the disturbance, and domain of influence is where the disturbance may be felt. So like in this elliptic problem the entire domain is domain of influence, whereas when you have a time marching problem, when you have t equal to t0 is the time over which the disturbance is imposed, t greater than t0 will signify the domain over which this influence will be felt. So any event which is t less than t0 will be the domain of disturbance, right, that especially here it is t equal to t0 where you have the location of the disturbance initiation, and that initiation of disturbance will be propagated in a direction forward in time. So you have only one discontinuity here and that is how only one real characteristic. So the only one discontinuity is with respect to the time equal to 0 or reference or t0 condition, which we call as an initial condition. So you have at t equal to t0 some condition, say at t equal to t0 you have the entire temperature of the rod at 0 degree centigrade. Now with respect to this there is a discontinuity at t greater than t0 because of this disturbance imposed at one of the boundaries. So that is a parabolic type of problem, but it is not as simple as that if you just consider it to be of parabolic nature and forget about the other type of behavior. If you consider a case of a heat conduction problem where time tends to infinity, and when you say that time tends to infinity there are many problems which at large times reach a steady state. So maybe there is a transience over the initial period of time, so if you allow this system to evolve with time the system can attain a steady state. When it attains a steady state there is no more a derivative of temperature with respect to time, that ceases. So once that ceases it will be just d square phi dx square equal to 0. So then that will be just like a Laplace equation prototype and it will become a boundary value problem or an elliptic problem. So we can say that this problem also has some elliptic nature inbuilt with it in the steady state limit. So it is better not to say that it is a parabolic equation. A more correct way of specifying this type of equation is that this is parabolic in time and elliptic in space. So it has this nature which is like an initial boundary value problem because you have to specify the initial condition and over and above that initial condition is the occurrence of the discontinuity because of the disturbance that is being imposed, but when the disturbance is imposed it still propagates in all directions at infinite speed. So that elliptic nature is also retained. So it is an initial boundary value problem. So combination of initial and boundary value, and it is basically parabolic in time and elliptic in space, elliptic in S. So it is essentially a time dependent problem physically with a significant amount of dissipation. So the dissipation is occurring at a very rapid rate so that the system will try to homogenize any disturbance that is being imposed on it over some boundary or at some interior point. Now regarding the time marching or a one way type of coordinate that the time essentially manifests itself, it is also possible that space itself manifests like a one way coordinate. Let us take the example of boundary layer development over a flat plate. So, if you consider that there is a flat plate over which you have the development of a boundary layer, you can clearly see that if you use the boundary layer coordinate, then along the x direction you have the growth of the boundary layer delta, which is a function of x, or any other variable which is a function of x. So, it is just like a marching problem, that as you march along the axis of the plate it grows, and it is a open towards infinity in one direction. So, if you have x equal to 0, you have your domain from x equal to 0 to infinity theoretically. Of course, practically the plate is bounded by a finite limit, but in principle you can go up to infinite length along x, but you cannot go to negative x. So, your origin of the problem is starting from x equal to 0 towards open infinity at x tends to plus infinity. So, that is like a space marching problem, that you are marching only along positive x, and whatever is happening at some x is not influencing what is happening in the back. And why that is possible? It is possible because this boundary layer theory you are developing for high Reynolds number. So, inertia force is very strong. So, essentially what happens, viscous force is a force which tries to propagate its message in all possible directions. So, if you have a momentum disturbance, that momentum disturbance tends to propagate in all possible directions at infinite speed, that is the effect of viscous force, whereas inertia force is like an unidirectional effect, because inertia force is very strong for boundary layer types of flows. So, what you are having, because these are high Reynolds number flows, so there will be predominant direction of propagation of disturbance in the forward x direction along which it will march. So, there if whether there is some viscous effect, that there is definitely some viscous effect, but viscous effect will not be propagating towards or will not be propagating this entire flow towards the other direction until and unless there is boundary layer separation. So, if there is boundary layer separation, then this entire discussion is not relevant, but until and unless there is boundary layer separation, it is a unidirectional way in which the message is propagating from the left towards the right, and that is a sort of a space marching type of situation. So, when you are designing a numerical scheme, here you can treat this x like time coordinate, where you are marching along positive x, and for each and every new positive x it is influenced by what was the event in the old x, but the new x event will not influence back what is going to happen in the old x, because of a predominantly unidirectional nature of the flow with a high inertia. Let us consider a third example. So, what is this example about? Just we considered one example where it was a steady state heat conduction, another example where unsteady state heat conduction. This is an example of maybe a wave propagation, or we can say that physically an example where you have a string which is tied at the two ends. Now, you create an initial disturbance by giving some initial displacement and initial velocity to it, and then release it. Then what will happen? The string will vibrate, and its displacement will be governed by this equation as a function of position and time. Now, the question is, that what type of equation is it. Let us try to assess that. We will assess that subsequently. So, to do that, let us first try to identify the nature of the characteristics of this equation. It is possible to write this in this way. Let us say that we give a name, small x is nu capital X and small t is nu capital Y, just so that we can formulate it in this form. Equal to some function. So, what is a here? Minus c square. What is b? 0. What is c? No, you have to bring all these terms in one side. So, it is not 1, it is minus 1. No, c square, this one minus this is equal to 0, that is the equation. Okay, a equal to plus c square and c equal to minus 1. Okay. Then what is b square minus 4ac? So, what is the characteristic dy dx? B is 0, so plus minus 2c by 2c square. So, plus minus 1 by c. What is capital Y? Capital Y is t. So, you can write this as dt dx is equal to plus minus 1 by c. That means dx dt is equal to plus minus c. So, if you integrate it, you will get x is equal to plus minus ct plus some c1. So, you can find out the characteristics by first you can forget about this c1 because it is just an addition of a constant, it will shift only the line by a constant, but the main functions are x minus ct and x plus ct. These are the two characteristics. So, one is x equal to plus ct, another is x equal to minus ct. Of course, x equal to plus ct plus c1 and x equal to minus ct plus c1. So, but if we forget about that c1, the functional dependencies, one is x with plus ct, another with x with minus ct. So, these are the two characteristics. So, you can see that here the effect is not a function of time only, it is not a function of position only, it is a combined spatiotemporal effect where you have a new variable, let us give it some name, say zeta and eta. These are called as characteristic variables across which you have possible discontinuities, and these zeta and eta are combined functions of x and t. Not only that, it is possible to write the solution of this equation entirely in terms of this characteristic variable zeta and eta. So the role of the characteristic is very interesting. The characteristic not only shows the possibility of discontinuities across certain lines. So across the lines x, family of lines x minus ct and x plus ct, there can be possibilities of discontinuities. In the next class we will see through examples that how such discontinuities may be physically originating and how that relates to the physical property of these equations. Of course, because you have two real characteristics, this is a hyperbolic equation, and hyperbolic equations have certain interesting features. These features are not evident in the parabolic or elliptic equation. So we will understand these features very carefully, because some of these features are very important in high speed compressible flows, and these have lot of relevance in fluid mechanics numerical simulation. So we will look into that carefully, but more importantly what we will try to understand first and see that we can write the entire solution in terms of the two characteristic variables. So the characteristic variables play such roles that in terms of those you can write the solution, and those variables signify locations of certain lines across which you could have possible discontinuities. When we say discontinuities, in the next class we will try to understand that what is the origin of that discontinuity, where from that discontinuity comes, and are those the only lines across which you have discontinuities. These are important questions that we have to clarify, because if there are lines beyond these characteristic lines across which there are discontinuities, we have to accommodate that also in the numerical method. So we will identify that these are not the only lines across which you could have discontinuities. You could have discontinuities across certain other fronts which we call as shock fronts, or the corresponding discontinuity is known as a shock wave in compressible flows. So we will try to understand where from physically that comes, and for each and every case we will try to relate that physics with the corresponding mathematical behavior of that partial differential equation. So we stop here today and we will continue with this in the next class. Thank you.